Hi, welcome to this special edition lesson for the end part of calculus, which I'm going to be calling the antiderivative. Well, actually, many people in the past have called it the antiderivative, so there's nothing special about me calling it that. So we've talked about derivatives a lot and differentiation, and there's another part of calculus that is called integration. And the base form, the very basic foundation of integration is called antidifferentiation. So finding the antiderivative would basically be finding what the original function would have been had you been given the derivative. Okay, so generally we consider or we denote the antiderivative with an uppercase F. So this uppercase F is the antiderivative of lowercase f on an interval. This is just all mumbo jumbo. If the derivative of the antiderivative is the function you're given. So if we see that if we're given the main function or the antiderivative, we see that it's uppercase f of x, which is x squared, then lowercase f of x, which is the derivative of the uppercase, and actually this can actually be written as f prime, uppercase f prime of x, is this, and we see that that's 2x. Okay, we notice that, of course, with the derivative, you subtract 1 from the exponent when you bring the exponent down in front. Okay, so we've seen that before. If we move on to x cubed here, we know that the derivative of this antiderivative, uppercase f of prime of x, is the derivative f of x, and we see that that's going to be 3x squared. Okay, so each time we're subtracting 1 from the exponent when we take the derivative. If we go the other way, then uppercase f of x is the antiderivative of lowercase f of x. So if when we take the derivative, we subtract 1 from the exponent, then going in the opposite direction, we would be adding 1 to the exponent. Okay, so if the derivative is x cubed, then the antiderivative would have to be x to the power 4. Okay, and notice that, so now if we test this and we differentiate this x to the power 4, and we look at the derivative that we've been given in the first place here, we see that differentiating this would give us 4x cubed. So the antiderivative of 4x cubed is x to the power 4. If we differentiate 3x squared, then the derivative is going to give us, well, 3 times 2. That 2 comes down in front. So we're actually going to have 6x, and of course to the power 1, because we subtract 1 from the exponent. So here, that actually came from 3 times 2, right? The coefficient that we were given at the beginning multiplied by the exponent that came down. So sometimes we have to kind of take into account, well, what's there and how did we get that? So if we now look at f of x equals 4x, well, the exponent on x is 1. So if we're going to take the antiderivative, we have to add 1 to the exponent. Okay, and well, we see this as 4 here. If we differentiate this x squared, the 2 will come down in front, but we're ending up getting 4. So it would normally be 2x, but here we got 4x. So that must mean that there was already a 2 there at the beginning. Okay, there's already a 2. So now if we differentiate this to check our values, we multiply the 2 times 2 to get 4. We subtract 1 from the exponent to get 1 in the exponent there. Okay, so we have to sort of see what was given to then see how we can get that when we would eventually differentiate the antiderivative. With we got 5x to the power 5 here. So we know that now with this pattern, we're adding 1 to the exponent. Okay, so we've added 1. Now if we differentiate this, the 6 is going to come down in front. Okay, but this is just 5. So how do we get a 5 out of this if we're bringing down a 6 when we differentiate? Well, that 6 doesn't appear over here in the derivative. That's not there, but there is a 5. So what if we multiplied by 5 over 6? Because if we then multiply the 6 down in front, the 6 divided by 6 cancels, it becomes 1, and we're left with that 5 in the numerator. So differentiating 5/6 x to the power 6 will give us 5x to the power 5. Okay, so we have seen also when we're taking our derivatives that we subtract 1 from the exponent and we bring that exponent down in front. So we've got our n multiplied by x to the exponent n minus 1. Now if we go the other way, okay, so this is what we've seen in the past. If we go the other way, well, we have to add 1 to the exponent. So that would be x to the power w plus 1. Well, if this coefficient here is 1, we have to multiply, we have to put something in this coefficient here so that when we differentiate and we bring that exponent down in front, that is going to cancel out and just give us 1. So if we're multiplying by w plus 1 when we differentiate, what would we have to do to make that a 1 in the for the coefficient? Well, if we know this is x to the power w, and this was w plus 1, well, we know that w plus 1 had been multiplied down in front. But in order to get a 1 there has to already be a w plus 1 in the numerator. So w plus 1 over w plus 1 equals 1. So what we have to do over here is we have to make sure that there's a 1 over w plus 1 in the coefficient, and that will negate this w plus 1 when it comes down in front. Okay, so for our general derivatives, we always have this n in front, and the n, we are always subtracting 1 from the exponent. For integration or antiderivatives, we have to add 1, and we multiply by the reciprocal of the new exponent. Okay, so that's going to be our new the new formula or the process that we will be following anytime we do this, anytime we take the antiderivative. Notice here, the new exponent was 6, and here we divided by 6, or we multiplied by the reciprocal of that new exponent, which was 6. Okay. All right. So now we have to take a look at these special cases. So when you remember when we differentiate sine x, we get cosine x. And so here the derivative, so of course this side is always the derivative of our antiderivative. That derivative gives us cosine x, so that means that the antiderivative had to have been sine x. So if you differentiate sine x, we're going to get cosine x. When we look at this negative sine x, well, if we differentiate cosine x, we get negative sine x. Okay, so these are the antiderivatives of these values over here. So we always have to test ourselves to make sure we see what we need to differentiate to get the original question that we're given in the problem. When we have sine 3x, well, this gets a little tricky. Okay, so we got a positive sine x. So when we differentiate, we know that we're going to have a cosine 3x. So the derivative of cosine 3x will give us negative sine 3x. So we have to make sure that we have a negative in front here to make this positive. And then when you differentiate, remember we differentiate the trigonometric function followed by the product of the derivative of the angle. And the angle right now is 3x. But here there's just a coefficient of 1. So we also have to multiply by the reciprocal of the angle, or the coefficient of x in the angle. So then now if we differentiate this, the negative cosine 3x, differentiate negative cosine becomes positive sine, or negative sine of 3x. The angle still stays the same. And then if we differentiate the 3x, we get 3, and 3 multiplied by 1 over 3 is going to give us the 1 that's in the numerator here, which will give us that 3 over 3 that we need for that coefficient. The derivative of e to the x, well, whether we differentiate e to the x or find the antiderivative of e to the x, is still just e to the x. And the same sort of thing happens when we differentiate an exponential as it does with the trigonometric functions. We have the original e to the 3x, but again, when we differentiate this, we're multiplying that by the derivative of the exponent, which in this case is 3. And here we see we've got a coefficient of 1, which means, again, we have to multiply by the reciprocal of the exponent. Then if we differentiate this to check, it's e to the 3x multiplied by 3, because that's the exponent, the derivative of the exponent. 3 times a third gives you 1, which is that 1 that we see in front of the e to the 3x there. Okay, so anytime you find the antiderivative, it's always very, very advisable to differentiate what you found so that you can just test to make sure you've got the right antiderivative. Now, if we take a look at this here, like in the last page, that table, we didn't look at anything where there were constants involved. So if our given function f of x is 2x, then the antiderivative would be x squared, because of course the derivative of x squared is 2x. But if you differentiated x squared minus 3 or x squared plus 4, the derivative is also 2x, because the derivatives of those constants just become 0. So there's an infinite number of antiderivatives of any function because, well, this is a vertical translation, right? So the function could be like this, it could be up here, it could be down here. So if we have any sort of, sorry for the crude drawing there. So anywhere along that line, along any vertical translation, the antiderivative will still be, it'll be x squared, but it could be anywhere along that, could be any vertical translation, because the derivative of each of these, the gradient or the slope of the tangent is still going to be the same. So that's the derivative. So the derivative is going to be 2x for any one of those. Doesn't matter where they are translated. So that's why we always have to add in a constant, and this constant is always added in here when you take the antiderivative, and that gives you the most general form of the antiderivative, so that you can just be a little bit more thorough with what your antiderivative actually would be. Okay, so we always have to add in that plus c, which would give you any imaginable translation, vertical translation to that function. Okay, so here's a table of popular antiderivatives. So if the function is 0, then the antiderivative of that would be, well, 1, because the function is the derivative, and the antiderivative is the original function that it could have been. if the function, the given function, and this is, we're calling this, this is our f of x, and then this is our uppercase f of x. They're on opposite sides of the table from the one that we saw on the other page, unfortunately. And so then when we've got x to the power n, the antiderivative of that is you add 1 to the exponent, and then you multiply by the reciprocal of the new exponent. Okay, so this is always the new exponent, or the new power, whichever you like to say. But you always have to recall that you're always adding 1 to the given function to get the antiderivative. E to the kx is 1 over k e to the kx. Again, we're taking the reciprocal, we're multiplying the reciprocal of the coefficient of x. Same thing for cosine and sine. We're multiplying by the reciprocal, and that will negate the derivative of the angle. Okay, and these are just simple ones where we have like a linear function in the exponent for the exponential function or the trigonometric functions. That's why we just got 1 over k. It gets a little bit more complicated when we have other functions like quadratic or cubic or whatnot. So these will work for just regular linear functions that are in the exponents or in the angles of those trigonometric functions. All right, so let's just take a look at a couple examples here. And this is just a general overview. I just wanted to give you some exposure to antiderivatives, just so that you see how they work a little bit before moving on to any post-secondary work that you may do. Okay, so the function is 2x squared minus x plus 7, which would be sort of the derivative of the antiderivative. And so for each of these things, we know that we've got 2x minus x plus 7. So the exponent on this 2 increases to 3, and then we have to divide by the new exponent. When this is x, the new exponent is 2, and then we have to multiply by the reciprocal of the new exponent. And then this is x to the power 0, technically. So then this would be 7x to the power 1. Of course, we could multiply by the reciprocal of that, but that's just 1 anyways. So then just to check to make sure it's all correct, you differentiate this. So 2/3 x cubed, the 3 comes down in front, you get 6 over 3, which divides to give you 2. You subtract 1 from the exponent to get x squared. Okay, so that one checks out. You differentiate this, the 2 comes down in front, 2 times a half is 1, which is the coefficient of that negative x there, and the new exponent is 1. And then the derivative of 7x is just 7. Okay, so that one checks out quite nicely. Same sort of thing here. We've got cosine x negative sine or minus sine 3x. Well, we know the derivative of sine x is cosine x. Okay, so that doesn't have to change at all. So derivative of sine x is just cosine x, that's fine. Then the derivative of cosine 3x, well, that's going to be negative sine 3x. So we can leave this as positive because the negative comes out when you differentiate cosine. And because the coefficient of sine there is 1, that means we have to multiply by 1 over 3. So when we take the derivative of this, the angle, that 3 comes out and multiplies by the 1/3 to give that 1 as the coefficient for sine x there, or sine 3x. Okay, so that one checks out nicely. Again, we'll do part of it and then just kind of make the adjustments we need to make. So 3e to the negative x, because the derivative and the antiderivative are the same for the main function. So the antiderivative, Well, if we differentiate 3e to the negative x, we get 3e to the negative x. And then we multiply by the derivative of the exponent, which in this case would be -1. So that negative comes down in front there. So that's why this stays positive as the antiderivative, because when you differentiate this, the negative will come down in front to give us that negative for the derivative. And then again, here we've got e to the 2x, so that's going to be constant. And so when you differentiate e to the 2x, you get e to the 2x multiplied by 2, because that's the derivative of the exponent. That comes down to multiply with the coefficient here to give us 6. So that means that there must be a 3 here to differentiate to get that 6 in front when we differentiate the antiderivative. Okay, so that one works out. Oh, sorry, and you know what? I've forgotten all the way along. We have to add c to all of these. I got so wrapped up in their actual antiderivatives, so I forgot the plus c. Now for these ones, I'm actually going to rewrite this as 6x to the negative 2 minus 5x to the negative 3. And I'm going to do that just so it'll make it a little bit easier to see what we have to do here. So again, we're now adding 1 to each of these exponents. So x to the negative 2 will become x to the negative 1. And x to the negative 3 is going to be x to the negative 2. Now, if we differentiate this, the negative 1 comes down in front, and we multiply, we end up getting a positive 6 there. So this has to be already a negative 6 in front there. So when you differentiate this, negative 1 times negative 6 gives you positive 6. Subtract 1 from the exponent to get x to the negative 2, which is what we have there. And we can then return this to the same form that we were given. And then here, we differentiate x to the negative 2. That comes down in front. We've got the negative, so this is going to be positive here. But we get a 5. So when you bring down that negative 2 to differentiate and we get a 5, that means that there must already be a 5 there already, divided by 2. So then when you bring that negative 2 down in front, the 2 over 2 becomes 1, leaving us with 5, and the negative changes that positive to a negative there. And then we add c. And then I'll just change this back to its form that we were given in the original question. And of course, the derivative of each of those c's each time will be 0. Okay, so that is a little quick run through of antidifferentiation. It does get a little bit more complicated than this, but this is at least a little first view of antiderivatives so that you can perhaps use them next year if you need to. Okay, so thanks for watching, and we'll see you in class.